Hello, I am Alexandre Mateus. I will show this work with the title Structural Static Analysis of an Academic Rocket Engine using 6061 aluminum with 1020 steel. This work was elaborated by Alexandre, Ayesha, Ayrton, Vinicius, Helder, Vitor, George Santos Marinho at UFRN. Summary. In the methodology, we'll be talking about the model used for analysis, materials and their properties, boundary conditions, mesh structure, convergence test, analytical and numerical analysis, and the results, convergence test, structural analysis of the von Mises, displacement analysis, comparison of results, conclusion, acknowledgement, and reference. Introduction. The first appearance occurred in the 13th century when the Chinese created a device for military using gunpowder. After the Middle Ages, with the explosion of study in the areas of math, physical, and chemistry, the idea of a travel to space became something possible in the scientific community. However, a rocket needs a heavy investment and high security. Therefore, this work has objects like use numerical computation methods to simulate the use of different materials, steel and aluminum, in a rocket engine, reducing the weight given this association, proving to be safe. Methodology. Analysis model. Here the representation of the analysis model projected by pressure visual equation for the determined the nozzle thickness, envelope and bulkhead being screwed together. Figure 1 model used for simulation of the assembly Poty G. Still in the analysis model, it is possible to see the dimensions used for agent component. Materials and their properties. Table 1. Physical and mechanical properties of the materials used. Properties. Yield stress, model elasticity, Poisson ratio, breaking stress. Software and consideration. The software used were SolidWorks and Ansys AIM, where the first was for modeling and the second for simulation. In the static analysis, the effects of temperature were disregarded, as it has a very abrupt burning, and the screws were considered cylinders in order to simplify. For the border conditions, the fixation was on the bulkhead as it resembles the practical situation of a static test, and the maximum internal pressure was 3. The contact of the bulkhead with the envelope and the nozzle with envelope were considered without separation, no separation, because it allows longitudinal movement without separating. The contact of the screws was considered glued or bonded, since the screw is fixed to the nozzle with the envelope by means of threads, as well as in the bulkhead with the envelope. Figure 6 representation. Mesh structure. In choosing the mesh used, the resolution and overall size were chosen. The convergence test consisted of the variation of the maximum tension of the knife in the entire body analyzed as a function of the number of elements. The criterion for mesh convergence when the variation has become stabilized. The method used was the finite element method, which from Mrs. they are being considered as a criterion. Through the equation shown, we can see that the von Mises stress will be a function of the longitudinal and the circumferential stress of the knife, be considering the pressure vessel through thin walls. Stress 2 means radial stress, which is 0. Finally, safety can be calculated by the resistance for the flow of the material taken from the properties table divided by the stress of von Mises. In addition, displacement analysis was performed with the by mathematical reduction, where the displacement can be given by the force multiplied by the initial length divided by the modulus of elasticity times the area of the cross section. Results and discussion. As stated before, the number of nodes in the convergence test was varied, reaching a high resolution global curvature sizing, being the most suitable for structural simulation. It is observed by the graph that when it gets close to 55,000 elements, the graph becomes constant, being considered approximately 97,000 MPa. The analysis by von Mises in the nozzle figure 9, the highest tension was approximately 73.3 MPa of maximum tension and approximately 70 MPa for the bulkhead. Both stresses are superior to the resistance to the flows of aluminum, recommending the use of superior material it is possible to identify more intense stress as produced in the region of contact between the screws and the bars, represented by the yellow color. As for the envelope, the highest stress was 53.6 MPa, which is less than the aluminum flow stress, meaning that it is possible to use this material in this case, reducing the overweight of the component, a favorable point for the aerospace. Likewise, in the region of the screws, the tensions were more accentuated due to the internal force of the envelope, contrary to the fixing screws. In the displacement analysis, the largest displacement was at X, being located in the nozzle mainly, as expected, being very small. is in figure 11, being 0.033 mm, not warning for the project. Comparison of results. Comparing the result with the other materials, we see that aluminum would provide less weight for the envelope, still providing security, and the carbon steel is recommended for the nozzle and pH. The materials can also be compared in the terms of age, safety, quality, time, and financial viability. The minimal values used and recommended by the DIN are 1 mm ticket, which would therefore be an alternative to structural design with aluminum. Thus, we can conclude that static simulation proves that it is possible to guarantee structural safety with less weight. It is possible to use an aluminum alloy envelope in rocket engines. The pressure in the screw region was more intense. The displacement in the nozzle is more intense. Recommended to use more resistant materials in the nozzle and bulkhead. A comparison with a practical static test is suggested. Acknowledgement. This article could not be completed without the help of several key elements that contributed directly, starting with Ansys AIM and SolidWorks software, Heat Transfer Laboratory, and the Mechanical Engineer Department at the Federal University of Rio Grande do Norte, Advisor Jorge Santos Marinho, and the Poty G rocket design team. These are the references. Thank you and see you later.